Okay, so we're going to look at a few of these problems. Tomorrow's quiz will have about 10 questions. They will not be the really, really hard ones. I might give you one really, really hard one for a bonus. Okay, so you can expect about 10 questions that you should be able to do relatively easily. Maybe there'll be one in there to stump you, maybe not. Okay, we'll probably take about 15 minutes. Okay, so and then the questions 34. 36. So let's look at some of these, and the rest of them you're finding okay on the answers? Are we finding them? Okay, 36. What y'all do to start it? Who started it? What'd you do to start it?
I said we're gonna do 20 and did that whole.
Okay, so all right, well, let me move that up there. We're gonna do this, and every time it's even, I use 2. Okay, you don't have to, but I always do. You could use 4. 4 is a perfect square, so that's nice, right? I'm gonna do it with 2 just because it's even, and that's the way I always do it. Okay, so this will be 2 into 3 is 1. You'd have 1 left over, so 12. So this is 160, right? Okay, and then 2 into 160 is 80. And then you could go, what goes into 80? It's still even, so 40, 2, 20. I'll do it with all the prime factors to start us out. 10, 5, as long as it's even, I can continue dividing by 2. So what I came up with is 2, 6 times 5, right? Okay, for each 2 times 2, I actually have 4, right? So this is 4 times 4 times 4 times 5, right? That's another way to write that number under the square root. So I'm going to rewrite it so it's equivalent with those numbers. 4 times 4 times 4 times 5. This is not the only way to do it, okay? This keeps me from having to write down 6 times, okay? And you may not have done this. You might have used 16 times 20 in the beginning, right? 16 times 2 is 32, right? Okay, we'll do it that way in a minute. So this is a good question. So when you do the square root of 4, it's equal to 2. So whenever you do the square root of 4 and it comes out, it's 2 and it's multiplied by that 4, okay? So when you read this 4 square root of 320, it should be 4 times the square root of 320. We don't often say times, but that's what we're doing. And so we're going to do that over and over here. Square root of 4 is another 2 times in the front. Square root of 4 is another 2 times in the front. Square root of 5, I don't know that. So what I've done right there is still equivalent to this. So you want to make sure whatever you write is equivalent to what you had before. Okay. So now I know the answer is whatever that is times the root 5. Okay. So this will be 8 times 4 is 32 square root 5. Okay. That would be my answer. Okay. Now I could have done 16 times 20. Did anybody think that way? 16 times 20? No? Anybody think any way about this problem? You come out with any number? Daniel, what you come out with?
Times 5.
You thought of that?
So I'll just think of another way to solve it.
Okay, so let's do it that way too. So most of us can't think of that though, but it's not bad to know those perfect squares are probably in there somewhere and you can always kind of guess and check, right? So let's do it both ways. 64 times 5, 64 being your largest perfect square that goes into 320. That's the one you want, okay? Notice when I rewrote it, I left the 4 sitting there. You don't want to forget about it. What you write down needs to be equivalent to what you write down up here. So don't feel like you're working on this piece and you're going to go back and get it. You want your steps to make sense, okay? So at that point, you would go, that's 8 times 4, so 32 root 5. Okay? Yes.
So what do you take out of 320 when you do that? Like that first number?
This way,
no, the, like,
16?
factor.
Back here.
Say that again?
32 root 5 isn't back here.
It's not back there.
No, it's 30.
Here it is, right here. That's all right. What do you mean, Parker?
So can you take like, you can take 32 out of 320,
Okay,
can you take like 10?
so if you wrote it 4 times the square root of 32 times 10, is that what you're saying to me?
No, I'm saying, like, you take, instead of taking 32 out of 320, you could take 10.
So say 10 times 3, 32?
No, when we do like the, what do you call
This factoring
it?
thing?
Yes,
You want to divide by 10?
yes,
Okay,
can you do that?
you can, you're gonna get 32, right?
Yes,
Okay, so that would be the same thing as that, right? So if you were trying to factor, like you were saying, and divide by 10, you're not dividing by a prime doing that, right? Which means it doesn't really help you because unless you want to sit there and go, oh, well, that's 5 times 2. That's 2 factors, right? Does that make sense? So
you have to do it by prime.
well, it's easier to do it by primes because you're looking for a pair of primes because 2 times 2 is going to be equal to that perfect square, right? If you get 5 times 5, you're going to have some perfect square, 25. And if it doesn't show up twice, then you have numbers that are prime and they're going to be left under the radical. Does that make sense? Sort of. So let's just say you did that. Then you should say 32, I don't know the square root, 10, I don't know the square root, so I gotta do something else. So you would go 4 square root, what's 32? What times what?
8 times 4.
Okay, 8 times 4. Well, 4 I know the square root of, so I'm getting there. What's 10?
2.
5 times 2. Okay, I don't know the square root of either one of those. Okay, what do I know about 8?
It's 4.
Okay, so you would get to this point doing what I've done. Are you good with that? So far? Okay, so at that point, you could say that's 2 times 2 on the outside, right? Okay, but I've got 2 2's, 2 2's, and 2 times 2 is 4. So when I do the square root of 2 times this 2, I get a 2 on the outside, right? So this is a 2, this is a 2, and that's a 2. So then you see I'm getting 3 2's coming out.
Yes,
Does that make sense?
yes.
So you can go through this a lot of ways. If you can come up with this large number, it's easier, okay? However, 64 times 5, that's kind of hard to come up with unless you're just really looking for those perfect squares. So you could be a good guesser and go like, I know the squares are 9, 16, that's 25. 36. Do any of these go into my number? You could do it like that, right? Okay, you don't like that problem. Okay, y'all don't like that problem, huh? Okay, got another one? Okay, how are we doing? Are we getting most of them right except for that problem? Okay, you're gonna have one that's tough. Okay, we're gonna put this aside for a moment and talk about section 2 real quick. So we need to write down just a few ideas in section 2. You will go back and finish this when I get done talking. We will work a little bit more, okay? So go with me to, I'm gonna use the book real quick just to make some points to you about section 2, okay? Yesterday, we didn't have homework, okay? So you actually have 2 assignments today. Yes, that's a lot of work, but we're gonna work. And let's look at section 2. On section 2, page 12, there's those vocabulary words, okay? So we need to know what a postulate is. A postulate and an axiom are pretty much the same thing. And you're gonna know some of these things. But the big one that I'm gonna work on today is between. So we're gonna hit to, these are just our vocabs. We're not doing the construction part. But let's talk about a few ideas, okay? So first of all, this is section 1, 2. In geometry, we've already said there's some 3 undefined terms, right? Okay, everybody ready? Okay, in geometry, what are the 3 undefined terms? Say them out. Plane, okay, point, line, and plane, and those are things we just kind of know what they are. Okay, I am on page 12, if you want to join me, page 12, if you want to join me, okay? Point, line, and plane are terms that you just kind of accept that they are what they are, okay? A point is a spot in space, right, or a place. Okay, a line is something that connects 2 points, and we talked about some generalizations, okay? So in other words, there's some things we just kind of accept, okay? A postulate is like that. A postulate is the same thing as an axiom, and it is an idea that is accepted to be true without proving it, okay? And then in geometry, we actually do proofs. And so what you do when you do proofs later on is you take these ideas of postulates and you use them to prove other things that are not quite as easily accepted. And that's the whole idea of expanding what you know, okay? So I'm not gonna write this down. These definitions are in your book. But it's a rule accepted without proof. It's also called an axiom, okay? You should also know what a coordinate is, okay? The first postulate that they give us is called the ruler postulate. And it's pretty obvious, and I'm gonna have you write down the ruler postulate, and I'm gonna talk to you about what this is doing. Absolute value of A minus B. This is x2 minus x1. I'm gonna use A and B, okay? So you can write down that definition, but the first one we're going to talk about is the ruler postulate. Just so you have the idea of what a postulate is accepted to be true without proof. Okay, if you have a number line like this, from -3 to 5, how long is it from -3 to 5? It's pretty obvious, right? It's 8, because you're used to counting, right? Okay, and it's because this goes to 0, and this is 3, and this is 5, right? So this is 3 plus 5, right? So the distance, we'll call this little a, and this is little b, and I just use those letters because the ruler postulate, in some books, it says absolute value of a minus b. This is the actual distance. This is the ruler postulate, okay? They call it A, B, okay? I'm only putting A to represent that it's the variable representing -3, okay? So that I don't mislead anybody, I'm gonna put capital letters because we've said you need to name them with capital letters, okay? Now, I told you at one point that a segment has a bar over it, right? A line has a line over it with arrows. When you see this written like this and there's nothing over it, it always implies length or distance, okay? So this means how long is it from A to B? That's the notation for it. So if you see a problem that says find M N, I want to know how far it is from M to N, okay? That's notation, okay? So in this problem, the ruler postulate here would be to take the A value and the B value, which is -3 and 5, and just put them into this, okay, formula. -3 and 5, the minus is coming down. And then do what's in there, -8. And it is an absolute value, so it's a length of A, okay? So that's the ruler postulate, okay? It's kind of crazy. It's a simple idea, okay? But it helps us if we have something like, what if you wanted -2.18 and -1 1/2? if you had something like that, where the numbers aren't quite as easy to just kind of count them up, then you use the rule and you would go like this. My numbers are this. I'm subtracting a negative. Okay? Now you would set it up kind of like that. That's the point of it, okay? So if you run into something really ugly like this, you would just do this, and this would be positive, right? And then it's gonna be some number that's a negative decimal inside the absolute value, right? Okay, so this would become this. And then you would do the rest and get the value. So I picked some ugly numbers. You see how they are. Which means that inside here is negative, and I have 2.18, 1.5. I got to subtract these numbers and take the sign of that negative. Okay, so this will be 8, and 5 from 11 would be 6. So I get 0.68, negative 0.68. And when I take the positive value of it, I would get 0.68. Okay, so that's the point of the ruler postulate. Sometimes numbers are not nice. Okay. That makes sense? Okay, so that's not hard. The other main idea that I want you to be concerned about with is this is notation. What does it mean? That means, it means what? A to B. A to B or distance or length, right? It means distance or length. You got to know that. Means distance or length. What about it tells us it's distance or length? There's nothing over the top of it, right? Okay, so that's what that means, okay? So you're gonna see that kind of pop up places, okay? So let's talk about the problems, but before we do that, okay. Watch the clock, okay? We need to know the idea of between, okay? Between, B-E-T-W-E-E-N. In geometry, the word between implies collinear. Okay, so that's all I'm gonna write, okay? And then I'm gonna give you an example. So for instance, if I have a line with 3 points, this is A, B, C, okay? B is between A and C. That's implied by my drawing being a collinear set of points, okay? If I drew it like this, A, B, C, B is not between A and C, okay? This is not between by the definitions in geometry, okay? So the point of this is we know that from here to here, if that's 5, and from A to C is 10, we're going to know BC is what? It's going to be 5, okay? Because this little piece plus this little piece is going to equal the whole piece. You've probably seen that before, right? Seen that before? So in geometry, that little idea of saying this piece plus this piece equals the whole piece is called the segment addition postulate. Now, realizing that's a postulate, this is something we kind of accept. We accept the idea that if this is 5 and that's 5, they add up to 10. That makes sense, right? Okay. So, but later in proofs, you'll have to name that postulate. So you got to know what it means, okay? In writing, that would be the length from A to B plus the length from B to C is equal to the length from A to C, okay? So notice I'm saying no bars, no bars, no bars, because I'm talking about lengths, okay? Does that make sense? That is called the segment addition postulate, okay? So as you're working on this assignment from your textbook, okay, let me just kind of talk you through a couple things. It's going to ask you to do something like plot these points. Here's number 7. Plot the points in a coordinate plane, then determine whether AB and CD are congruent. What's the word congruent? Equal in length, okay? Congruent means equal in length, okay? It's actually one of your vocabulary words. So you need to know the word congruent means equal in length. Okay? So when it says, are they congruent? The segments A, B, and C, D are naming those pieces and saying, are they equal in length? That's what that's saying, okay? So you're gonna plot these points, -4, 5, -4, 8, and it's gonna look like this. You don't have to get real fancy, -4, 1, 2, 3, 4, 5, 5, that's A. And then you're gonna go -4, 8 would be up here, and that's B, so you're gonna draw that point. Okay, then you're gonna go CD is 2, -3. There's C. And you're gonna go D is 2, 0. And I wanna know, are A, B, and CD congruent? Are they? Yes, you know that because this is a vertical piece, right? And that's a vertical piece. So you can actually look at this and go, the length AB is equal to how much? 3, and the length CD is equal to 3. And so that means that AB is congruent. That's the symbol for congruent to CD. And here we're stating that, yes, they are equal in length. They are things that are equal. Does that make sense? So all of these problems with all these points, they're all easy like that, okay? You're doing some of them. Yes, ma'am. Show you back? Okay, do you follow what I just did?
Yeah, I'll just try.
Okay, and then when you do problems like finding FH in the next set, you're gonna be using that idea. So these are not hard problems, is what I'm saying. You're gonna be writing down going, oh, that's 5. Oh, that's 18. It's not hard, okay? All right, so like if I'm finding the length of FH in this picture right here, what do? I go 19 plus 7, I get a number, right? Okay, when I find FH in that problem, what do? What do? 19. What do? You just subtract, right? Because the long piece minus the short piece will be the other piece, right? Now, we're applying the segment addition postulate when we do that, okay? Here, we're just applying it. We're not really doing a lot with it, okay? So that's what you're doing on that section, but you will find out that part of this assignment is review and refresh. So you're gonna see at the end, you're doing some solve this equation, just algebra stuff, okay? We don't wanna lose our algebra, okay? So that's kind of how that goes, and that's what you're doing on that second assignment, okay? So you have about 12 minutes. Is everybody with me there? So that's what you're doing there. Let's go back to our radicals worksheets. I looked at it wrong. You got 3 minutes, okay? Let's go back to our radical worksheet. You pick me out one that's hard. Pick a couple that are hard. And I'm gonna stop the recording.